very on-time students. Good.
Yeah, why don't you do the introduction and then I will take over.
Ok. Alors bonjour à tous. Bienvenue à notre cours à option Scala, qui est en fait la première édition cette année dans notre école. On a le plaisir et la chance d'avoir cette année professeur Kai Horstman qui va en fait majoritairement vous enseigner dans ce cours. On partage le cours avec moi-même et puis Madame Boran, Fatemeh Boran, que vous connaissez peut-être, qui va assister quelques séances. Donc voilà, je pense que je vais laisser Kai en fait s'introduire aussi. Le cours, ça va se dérouler en anglais. Vous pouvez bien sûr vous exprimer en anglais, en français, comme vous voulez. Si jamais il y a quelque chose que vous ne comprenez pas, professeur Horstman, il comprend très bien français et puis il parle aussi français, mais pour votre intérêt, comme ça on fait le cours en anglais, je pense qu'il est excellent, sincèrement. Ça c'est bien avec tout ce que vous allez avoir, avec la documentation aussi, après ça va être tout en anglais, donc c'est que de bénéfices. Alors, merci.
Okay, thank you. All right, so without further ado, let me just go through this introductory slide. By the way, everything that I'm saying, I'm recording and I'll put a video on YouTube, so if you don't catch something and you just want to listen to it again, it'll all be there. And of course, this is such a small group, which is great. So any questions that you have, just raise your hands and ask right away. In English, en français, auf Deutsch, whatever you prefer. So we're here to learn about Scala. And so why Scala? So it's a kind of a new generation of languages that's really built to unify multiple paradigms. So if you think of C++, C++ is kind of a kitchen sink. You can program it in one way or another way, but it doesn't really do a good job in unifying those various levels. Whereas the unique insight in Scala is that if you unify object-oriented and functional programming, you get something that is bigger than just either one of them. Scala is statically typed. These days we have so many languages that are very nice to dash off something quick. JavaScript or Python come to mind. And so if you have something that's 10 lines long, then of course that's very liberating. But when you have 10,000 lines of JavaScript, then that strikes fear in the hearts of most programmers because so many things only go wrong during testing. And so you get warned at a time when it's too late and too expensive really to find those faults. So statically typing is a big win, particularly for large programs. Scala is called Scala because it is a scalable language. So you can use it from very simple scripts, and you're going to be seeing that in the first few lectures very much so. And one can build it up to very sophisticated libraries, but that are also still easy to use. And we'll see quite a bit of that. You'll be using libraries that you will see to be very sophisticated, and you may wonder how they were built. And I am afraid you're going to be left with that sense of wonder because we're not going to go into all of the details, but it'll become quite apparent to you that Scala is there to give you things of great power. The language was invented by Martin Odersky from EPFL, who happens to be the husband of my charming co-instructor. So you are very close to the man himself, and so I know a little bit about it because I wrote a reasonably well-selling book about it that teaches Scala to people who come from a Java background. It uses a different approach than what we're going to be doing in this course. I'll talk about that a little bit later. But so you have several people who are designing this course who really know quite a bit about this language. And so I think you'll find it a great opportunity. So the other reason why people love Scala is that it works with the Java virtual machine. I mean, the Java virtual machine is this big workhorse thing that powers so much of the the internet. And you might say, Java is getting a little old and stuff, but the Java virtual machine is very much alive and kicking, and it gives possibilities for deploying applications and for for keeping them alive that really is unmatched with just about any other infrastructure. So you may have seen, for example, Node.js becoming quite popular in the last few months and years. And so I must say, whenever I look at Node.js, I say, that's really nice, but in a very small way. It'll never scale. And sure enough, the people who start out with projects that use Node, they abandon it when work gets hard, and they migrate more often than not to something that's based on the Java VM. So these things are used for very big iron projects in industry. And so there's two ways of looking at Scala. Number one is, well, Java is evolving very slowly, and so Scala is just a better Java. And that's a good way of looking at it, and I wrote a book that pretty much explores that angle, and that says, here's how you can move from Java to Scala without having your head hurt. But hey, here we're in a university, and the whole job of a university is to make your head hurt. Because, otherwise, why would you be here to learn something? So the other thing that Scala is very good for is that it expands your mind and makes you think about programming in a different way, and without being so esoteric that you would say, well, that's just a weird corner that doesn't have any practical applications. It very much has practical applications. And so what I want to do in this course is make it so that your head does hurt and your mind expands, but in a context that is eminently practical, where you can see that you can put those things to use. So the way the course is going to work is we're going to have a short lecture and then a lab. So I hope you all got my email about us setting up the work environment for that. And then a break, well-deserved, and then another short lecture, and then a lab. So after each lab, about 15 minutes before the breaks, I will say, okay, now let's call it quits, and then we'll have a discussion about what we learned in the lab. I would like some of you to show off some of the things that you did and explain them to the rest of us in English or French, your preference. So the whole idea is that it should be very hands-on and that you should learn a lot by making a lot of mistakes, which is the only way that anyone has ever learned anything. There's some grading scheme here. So there's going to be some exams, and you're going to some labs, and then there's a project. And the way we're going to be doing the project is towards the middle of the course. We'll be spending time in class working on the projects, and of course, you'll have to spend up some time outside class. And each of you will work in a team with on something that interests you personally, that puts these technologies to work, and then you'll present what you've done at the end of the semester. So the other thing that I'm trying to make these things interactive, and so I asked, how does one normally do that kind of interactivity in Switzerland? Because normally I have a lecture room with like 100 or 150 students, and so there's no sense for me to ask to ask someone about the answer, because I know it's always going to be that guy, the smart guy in the first row, who's going to answer all the questions. So I usually use these things called clickers. But for 10 people, it seems ridiculous to use clickers. So we're going to be using these low-tech clickers that you're going to be getting right now. So what I want you to do is read through this question, pick what you think is the right answer, put that card in front of you so that no one else can see it, and then when I say now, you all turn it over. Okay, so we're having the silly question here as a, maybe not so silly actually, as a warm-up. So I was told by the dean that alumni from this program, students who graduate from this program, were asked what was the one thing that they wish that they had actually learned better in the computer science program. And so they all had pretty much there was a very clear majority answer. So what do you think? So pick an answer, turn the card so that no one can see it, No. So what you have to do, so the trick is you don't want anyone else to be influenced by your selection, right? So you make it, you put it down, and then when I say now, then you all at the same time flip it over. It's a ritual, so one has to practice. All right, now. Okay, so we have a C, another C, 2, 3. Okay, so we have 5 C's. We have 1B. It doesn't matter if I'm exactly off. So that's about right. The answer is, by an overwhelming margin, the students who came before you said they wished they had had more opportunities to give presentations in English. And there was a very simple reason for that, because on the job, that's what they had to do all the time. You'd think this is Switzerland, and they'd have to give the presentations in German. But no, the Germans in Switzerland don't actually understand German either. And so English seems to be the common language of the land. And so that's what they wished. All right. Another question. Let's just do the same thing one more time. I just want to know. Okay, now. So we have a whole bunch of people who know nothing about Scala, and we have several who are reasonably fluent. So to those of you who are reasonably fluent, in the first several lectures, we will be restricting ourselves to a narrow and somewhat strange subset of Scala. So, and I would like you to make every effort to stay within that subset. And you'll see why when I do that. All right, so let's get right into some Scala basics here. The other thing that I should also tell you is, in terms of truth in advertising, you will be learning a lot of Scala in this course, but you're by no means going to learn all of it. So there will be many unexplored parts of Scala, and you're going to have to learn to deal with that kind of level of ignorance, because it's a large language, and it does have its very complicated corners. And there are very few people who know everything about the entire language. There probably are a couple, but most people who use Scala successfully, they live in a part of it, and that works perfectly well. So I'll just give you a few of the highlights, and I'll assume that from your general knowledge of programming language, you're going to stitch together some picture of that. So we have the usual kinds of types: integers, floating point numbers, booleans, strings. We have the usual kind of arithmetic operators. It's a C or Java-like language, so they'll look familiar to you. Variables are declared by the keyword val. And those of you who know more Scala should note that you're not allowed to use anything but val at this point. So there's val that says, here's some value. Give the name of the value, and then you initialize it. Notice that you don't have to give the type of lucky number. The compiler realizes that 13 is an int, so lucky number must be an int. So that's a little different from C++ and Java. It's a functional language. You guys had a course in functional programming, right? The programming languages course, where you learned like Scheme or Haskell or something. Haskell? Okay. So you know all about functions. So you can have an object here that's a function. So let's look at the thing here on the right. This is a function that takes an x and it returns x squared. So it's the squaring function. The thing on the right-hand side is a value of type function. And in fact, it's a function that eats integers and returns integers. So you see the type here. And functions are values like any other, so you can put that into a variable. So we put it into this variable here, which is called square. It's the squaring function. So for those of you who remember a bit of the Haskell, you do the exact same thing in Haskell with one exception. In Haskell, you don't have to give the type of the parameters. Haskell can infer parameter types. And for technical reasons, Scala can't. In a nutshell, it's because Scala has inheritance and Haskell doesn't. Semicolons are optional. And So you don't have to put a semicolon here. You can, and I don't really know what's better style or not. You put him? Yeah, I never put him because of the global pixel shortage. So it's up to you whether you want to put them or not. If you don't put them, you do have to get into the habit that when you run out of room on a line, that you have to end the previous thing, whatever it is that you're working on, with something that tells the compiler that it's not finished yet. So just put an operator there, or if you have an opening parentheses or some such thing, then that works fine. So it's just like in JavaScript. I never put semicolons in JavaScript. Other people tell me that I'm a bad person for it. And so it's a question of personal opinion. Every once in a while, people complain that Scala is much more complicated than Java. But that's not quite true. In many ways, Scala is much simpler than Java. In Java, for example, you have a difference between primitive types and reference types. Objects are different from numbers. In Scala, that's not so. Everything is an object. So one, for example, is an object, and I can apply a method to it. So I say 1.to of 10, just like you would do in Java if you could. And that's a useful method that gives you an object of type range. In this case, the range of all numbers from 1 to 10. So we'll be practicing those range objects in the lab. I won't say much more about it. So 1 to 10 yields a range, and it's one of many, many collections that you have in Scala. So you know collections in Java. You have, what do you have in Java? You have lists. Something else comes to mind? There were lists, right? Yeah, there were sets. Yeah, good. So you have lists and sets. So what's in Java? In C++ you have vectors. No, not in the standard library anyway. Yeah, you have basic old arrays, right? And arrays, that's another thing, but Java is actually complicated. Java arrays are completely different from anything else. They have a different syntax, they have different behavior, they have weird rules about them. So Scala is more uniform, that all the collections are similar. And also there are many, many more of them. And so just any collection that you might ever want, it's there in Scala. So a range is, as you can imagine, just a contiguous range of integers. Then you have lists, vectors, which are like vectors in C++ or array lists in Java, and so on. So now we come to a very useful function called map. And actually, let me, instead of doing this here on the slide, let me show you this here in this worksheet. Scala is an interactive language, and it wants to be explored interactively. So let me make what's called a worksheet here. We first need to make a project. Unit 1. Once we have a project, we can put in as many worksheets as we like. New worksheet, sheet 1. And in here, we'll say val r equals 1 to 10. And now I save. And now you see here on the right, where it says, well, unfortunately it got cut off a little, where it tells you what the answer is, the range of the numbers from 1 to 10. We may want to know what happens if you put in a much larger number here. And at some point it cuts off the output. Just want to know. All right, so we're now going to take this thing here. I'll go back to 10. And now I want to transform it in some way. You do that with a method called map. And map takes a function. Is there any function that we know? Oh, yeah, that was the square thing that we did. So let me write square again. And that was the function that maps x as an integer to x times x. And so now I'm going to apply that function square. And then you can see what I get is a vector containing 1, 4, 9, and so on. So it applied the function to every element in the vector. That's something that you probably have seen in Haskell. You don't actually have to give the function a name, and it's not actually very common to do that. So most programmers would just write r.map of, and then put the function right in here. And for distinction, I'll cube it now. And then you can see here the vector of cubes coming out. Now, the map method works on vectors, but it actually works on ranges and any other collection. And it has the very nice property that when you apply it to a particular collection, you get back a collection that's, if at all possible, of the same type. So if you apply map to a vector, you get a vector back. If you apply map to a list, you get a list back. If you apply map to a range, well, then you can't get a range back because a range is contiguous, and if you map the elements, they no longer may be. And then you get back, I don't actually know. You get back you get back a vector, and on the left-hand side, you see the type is a Scala collection immutable indexed seek, and that is a code word for forget that you've ever seen this. Okay, so you just looked at the easy part. There's no point in trying to decipher the Byzantine complexity of these types. All right, so let's look at a more interesting case here. So here I'm looking at the numbers from 1 to 9. I'm squaring them. And then I map to the remainder modulo 10. And then I just get the distinct ones. So let's see what it is. And what I get is the vector containing 1, 4, 9, 6, and 5. That's as you'll see in the lab, that's what's called the quadratic residues mod 10. Those are the numbers that are squares mod 10. You may wonder why distinct, because I never told you what distinct is, and I won't tell you what a lot of these things are because I'm assuming that you can experiment by removing it and then see what happens if you don't have distinct. So you see there's some duplicates, and the distinct throws out the duplicates. So one of the things that's characteristic about Scala is that you have a huge number of these little helper functions that can make your code simple and easy to read. Notice as one of the somewhat bizarre syntactical issues, there's no parentheses behind distinct. Now I'll be the first one to say that I've always hated this particular feature. But what can you do? I didn't invent this language. Martin did. So the rationale here is that if you have a method that has no arguments and that does not mutate its argument, that returns a new result without changing the old result, in that case, the style is not to put parentheses. Now, I don't know if in this case one can or cannot put parentheses. So let's see what happens if I do put parentheses. Then that doesn't work. And for the life of me, I can never remember when to put parentheses and when not. So I always try it with both, and then I leave it alone once it works. There is a rule, and I can look up the rule, and I know the rule, but it's not worth learning. So that's a bit of an issue. If the function is declared without parentheses, then you can't put them in. If it's declared with, I don't remember. All right. So the rule of thumb, though, and that works in almost all cases, and if I thought hard enough about it, I could give you the 3 or 4 cases where it unfortunately doesn't, is if you have a function with no args that doesn't mutate, don't use parentheses. So now a good question to ask yourself is, if you wanted to do this kind of thing, figure out all of the distinct squares modulo some integer. How many lines of C++ would that take you? Probably like, I don't know, 5, 10, something like that, right? But it wouldn't take you 1 line, and so it's very nice that you can do this so concisely. So what makes all of this niceness tick? It's the miracle of functional programming. So in functional programming, functions are values. So the square function that you've seen is a value. You can store it in a variable. You can pass it to another function. And later we'll be seeing functions that generate functions as their results. Now in C++, can you do this? In C++, you have as values, you certainly have the primitive types, structures, and you have pointers. And that's really all, if you think about it, that you have in C++ with some technical fiddling around of finite size arrays. But that's basically the values that you have in C++. In C++, you do have function pointers. But they're not really as useful as they are in Scala, mostly because in C++ you cannot create new functions. You can have a pointer to an existing function, but you cannot create a pointer. You cannot have a function that returns a function pointer that's created at runtime. In a functional language, you can do that. And that there is a lot of power in that. So over here, I show you a couple of values. Here's 3.14. It's a value. I can put it in a variable. Oops. Here I have another value. The syntax here is a little odd. Just trust me that math.ceil underscore is the ceiling function in the math library, and we're not going to be worrying about the underscore. That's what it is. And then I can apply the function, which is now really not a function but a variable containing a function, to this value with a parentheses notation. I could do the same thing with a square. Let me do that quickly here. So up here you've seen me define square. And now if I say, what is square of 16, then it's going to say it's 256. But notice that this thing it's a val, it's a variable. It's a variable that happens to hold a function. If over here, if I were to change what square holds, then I would get a different answer. So functions can be anonymous, and most of the time we write these small functions as anonymous functions. So this thing here is a value that has no name. And now it sounds somehow weird for something to be anonymous, but hey, this number is anonymous, right? We haven't given it a name. And so there's no difference in the mind of a functional programmer between 3.14 and this thing. They're both values of different types. So, and you can put functions into variables, just like you can put numbers into variables. For those of you who already know a little bit of Scala, you may have seen, you certainly have seen how to define functions with the def keyword, but you're not allowed to use the def keyword for a few lectures, in fairness with those who are just starting out. So every function that we're going to be defining right now, we're going to be defining with val. So why do we do this? Because it often makes programs simpler and clearer. A function is a bit of behavior, and we give that bit of behavior to someone else. So like map, for example, what map does is it applies a function to everything that's inside a collection, to all these values, and you just pass that behavior, that what should be done in here. And notice that there is no loop. In fact, I'm not going to tell you how to write a loop in Scala for quite a while. When I first taught Scala several years ago, was in a programming languages course, and after about 6 weeks where we were building fairly complicated programs, and I was learning together with everyone else, someone said, Professor Horstman, is there a while loop in Scala? And my answer was, I don't know. Let me look it up. So we were able to program for 6 weeks without ever using a while loop. And I don't remember when's the last time I wrote a while loop in Scala. So, so yes, it does exist. And if it didn't, it would be easy to write your own. But it does exist. But we're not going to be using it for a while. So right now, our go-to tool whenever we want to do something is map. So why can't you do this in C++? Well, I guess you could. So here I have a version of map in C++. And it does kind of what the Scala version does. The one thing that you can't do in C++ is you can't call map with an arbitrary piece of code. You have to put that piece of code into a function first. So you have to use named functions in C++ whenever you want to pass a function to somewhere. And so that's not as nice. The other thing that Scala is nice about is that by default, values in Scala are immutable. It means you can't change them. And that sounds scary, but think about strings in Java. Strings in Java are immutable, and people have been living with immutable strings in Java for 20 years and have been quite happy with it. So, for example, when you call the toUpper, I think it's toUpperCase, I think it's a typo, toUpperCase method on a string in Java, it doesn't change the string. It returns a new string with uppercase letters, and that's always the case with the methods that we're going to be looking at in Scala. So when you call map, for example, it does not mutate the vector that it operates on. It gives you a new vector with the result. And everything that we're going to be encountering in Scala for the next few weeks is going to use immutable values. So those of you who know that it's possible to do mutation in Scala, hold that thought for a few weeks until everyone else gets to that. We're going to be seeing what we can do with immutability for as long as we can get away with. So you can never change a variable by assignment in the subset that we're using right now. You can never change the contents of a cell in a vector or a character in a string. You always make new ones. And that's good because when you don't mutate state, your computation is inherently parallelizable. So it can be automatically distributed over multiple processors. For example, if you had a big vector, an operation on it could automatically be split into operations on subranges of the vector. And in fact, there's a way of doing that, and we'll see how to do that later. And it's an important consideration because parallel programming is now upon us. You know, it used to be that everyone learned a little bit of a weirdness about parallel programming in the operating systems class. You know, on the theory that maybe you have to write an operating system sometime when you're stranded on a desert island, and then of course you would need to know about this. Nowadays, this computer here that I have here in my hands, my cell phone, has 4 cores. The one that I'm buying in a year is going to have 16 cores. And one has to keep them busy somehow. So it's up to the application programmer to start having to deal with concurrency. And concurrency is really, really hard. Those weird exercises that you did in your operating systems class where you learned something about contention and memory corruption, and you had to fiddle with locks and stuff, that's not something that you want to have to do as an application programmer on a daily basis. Immutability is the one big weapon that you have to make concurrent programming easy. All right, so now I've talked for more than for 20 minutes, so we'll start with the labs as quickly as we can. Here's how the labs work. That you find yourself a buddy, anyone who you like. Do we have an even number of people? That's right. We do. All right, so group yourselves in a group of 2. One of you is the coder, and the other one is the scribe. The coder runs this guy. The scribe runs whatever you use for writing up your answers, which if you're a right-thinking person is Emacs. I don't care what it is. And then you later turn them in. So you work as a pair, and when you get stuck, you ask your buddy, and then you ask me. You switch those roles each lab. Your grade depends on it. And you turn in, the coder turns in the worksheet. The scribe turns in the text file to this email address, and then we'll grade them all. Okay, so get going. Start the Scala IDE and just get going with this. It's always painful to watch the formation of the groups and the getting going, so I will leave the room and get myself a cup of coffee. And when I come back, I hope everyone is busy working on this. So, yeah.